Welcome everybody on Zoom, welcome everybody in the lecture hall to this new lecture, a new chapter of the course, starting with document stores. Before we do, I'd like to take some time for questions. If there is anything that you have to ask regarding MapReduce, Apache Spark, is anything unclear, anything that you would like to go more in depth on? Nobody in the lecture hall. What about Zoom? Does anybody on Zoom have questions on MapReduce or Apache Spark? No questions? So who is comfortable with MapReduce and Apache Spark? Okay, very good. So then I guess we can continue our exploration. And of course, you can still ask questions later if there is anything to clarify. And of course, you're going to have these practical exercises with Spark, first one entire week of exercises just with RDDs, just for you to experiment how complicated it is to work with RDDs. And then you have a second week of exercises with data frames and Spark SQL. And then you will see that it's actually easier in some cases when the data is homogeneous, then Spark SQL and data frames are actually much easier than RDDs. All right. So if you look at the structured stack, this is the good old stack of the 70s with relational databases. One way to look at it via syntax, if you come from CSV, is that you have a level of physical layer that is the bits. That's what's written to the disk with zeros and ones. On top of that, you can store text, which is just a specific way of creating files, can be binary or text, right? So you could use text, you could store the data as CSV, right? CSV is a natural syntax for relational tables. Then you can have a relational schema against which your CSV might be valid. And that's mostly about the attributes being correct and domain integrity, that the values within each column match the relational schema. And then what you get are queryable tables, all right? Now, with a few exceptions, and I have here SQLite in mind, that's not how relational databases work, right? I'm sure that you never saw a relational database where you store CSV files somewhere and then you read them with SQL, right? It's a bit different the way that it works, because in a relational database, you actually have to import the data to ETL, it's called ETLing the data, extract, transform, load, and then it's put into these relational tables. And then what a relational database system like PostgreSQL is going to do is that it's going to store the data in a binary proprietary format that is optimized and that's hidden from you, and you just interact with the data as a SQL. And in fact, if you want to export the data, I'm pretty sure some of you did it. You don't even export it as CSV. You actually export it as a SQL script. Who's already been doing that from PHP-MyAdmin, for example? Exporting a database as a SQL script. Nobody? Some of you. We have some hands, right? So this is typically what people do. And then you execute the SQL script in order to re-import the data. In fact, the exam for the course for the PostgreSQL questions are typically in the form of a SQL scripts like that. Okay. This is what you would have as a hypothetical data lake in a structured stack. You would basically have CSV. But now let's stick a bit to this relational model, relational tables. So we have a few properties that this data has. Relational integrity, meaning that you have the same columns everywhere. This is why you can actually assemble this into a table and you don't need to repeat the column names, unlike JSON. You have atomic integrity, meaning that you don't have tables in tables in tables in tables. Everything is flat. The only thing you have here is atomic types. Remember that distinction that we keep making between the types? I did it again yesterday. There's the atomic types, strings, booleans, numbers, and so on. And there's the structured types, objects, arrays mainly. We do not have any objects or arrays in there. It's just atomic types, right? So this is atomic integrity, and you assume this for the relational model. And finally, and that's the other part of the schema, in addition to the name of the attributes, is the domain integrity, where you have specific types, atomic, if you have atomic integrity. So string, integer, char3, which is a subtype of string with 3 characters, and date, okay? So we assign atomic types to each column. And then when we have that, we have relational tables, flat, homogeneous. Then we can start working with the relational algebra with projection, selection, joining, grouping, sorting, and so on, right? But on relational tables, we can view this as a logical versus physical model that's called data independence, where you have the relational model on top and you have potentially a syntax at the bottom, right? The syntax in that case would be naturally CSV. In the case of semi-structured data like JSON, we saw that you would have trees on the top, the logical level, and you would have JSON as a syntax. Then what we saw is that in case that you can validate JSON against a schema, you can actually drop the JSON syntax completely and replace it with a different format called Parquet, for example, which is more efficient than JSON, right? What that means is that this physical view here, you can swap it. You can put whatever you want as long as you keep the logical view. So the idea of the relational model is that this is one potential syntax, but you can also drop it and have instead some optimized binary format internal to every technology. So you have SQL, we did a brush up a while ago, select from where, group by having, order, limit, offsets, right? Where you can execute these queries. All right. But normally, everything that I've said here is not new, right? For whom is that not new? These are all things you've already heard many different times, right? So this is really just things that I've already said here. I'm just wrapping things up. So now if you look at the stack, in the case of tables, we pretty much have everything, right? We could store CSV files on HDFS, read them as data frames with Spark. We saw that yesterday, right? Spark read CSV, blah, 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 then you get a data frame. Of course, that data frame is going to be flat, right? Because it's a CSV file. There will not be nestedness, but it's still a data frame, right? A relational table is a specific kind of data frame. Then you can use Spark in order to query it. You can also use HBase. That's also a tabular model. And finally, we saw yesterday that you can use Spark SQL in order to query CSV files on a data lake, right? So this is an alternate data lake-oriented way to query relational tables. So we've already rebuilt all of that stack with tables. And in fact, if you think of what we've done yesterday in the second hour with data frames, I really didn't introduce much to you, because the data frames, we already covered them a few weeks ago in the data modeling lecture. So you already knew what data frames were. And SQL, we've already covered it as well in the second week of the brush up. So all I really did yesterday was tell you now with Spark, you can actually manipulate data frames and you can manipulate them with SQL. The details are just how you do it. This is really just about reading the documentation and finding the comments to do that, right? But basically, we've rebuilt the entire stack. So now you could use a relational database system like PostgreSQL for directly importing and querying data, or you can do it the data lake way, reading CSV file from the data lake and using Spark SQL to query the data. All right. Now, here's the thing. This works with data that is structured, relational tables, that is homogeneous and flat. At least that's how SQL was designed. But we saw that the data can be different from just homogeneous and flat, right? It could be that it doesn't fit in tables. And here we saw that the starting point that we used in terms of syntax was XML and JSON instead of CSV. We saw that with this, you get trees. So you no longer have tables, you have collections of trees. If you're lucky and you have a schema, that collection of trees is going to be a data frame, right? But we're missing things here, right? We don't have yet a way to index the data, a data store, like what would be the PostgreSQL for XML and JSON? We didn't see that yet, right? Some system that does it for you. We don't have yet a query language that will be next week for XML and JSON. So this is what we are doing now. We are trying to rebuild the same things we had with relational tables. Now we want it with semi-structured data. We already now know that a few things are different. If you look at this slide here, the way it's different from what I showed you previously with relational tables is that validation is optional, right? You can absolutely read JSON and XML with Spark RDDs or with MapReduce, and then do whatever you want with it. It's just a collection of JSON objects. So validation is optional. You can, but you do not have to validate. So there's two paths here. On the left, you can decide to validate, and then you have data frames, and then you query it. or you can decide not to validate. Then you work with heterogeneous data and you query it. Okay, now, whenever you want to build a system like an equivalent of PostgreSQL for a new shape of data, because that's what it is, a new shape of data, the first thing that comes to mind to any data engineer, let's call them a data engineer, is to try to hack around by using an existing system in a different shape, for example, PostgreSQL, and on top of it, try to make the new shape fit. So you could use a system that works with tables, and then you can try to store these trees as tables. In a way, that's kind of what Dremel is trying to do, right? It's trying to store trees in tables. If you look at the Dremel, what it is, it's tables with a definition level and a repetition level, right? These are tables. So it's a way to take a hammer and try to make it fit into tables. So there are ways that you can do that when you're really, really lucky. For example, if the data is super flat, then you can actually interpret that object as a row. The same for XML, right? So in that case, that works. You can make it fit in a table. If you're also lucky and the objects or the XML elements look the same, you can also make it fit in a table, right? So the same goes for a schema. You can take an XML schema, you can convert it to a relational database schema, right? Who agrees that this is equivalent, right? This XML schema here we can store it in a relational table. The same goes for JSONs or JSON schema, but here it's JSON. We have a JSON schema. It naturally fits as a relational schema, right? So then a lot of people actually try that. They say, okay, we don't need to invent new things. Let's just use a relational database. The problem is that what they don't see is that this is a specific use case. Here we are lucky, first, because the data is flat. There is no nestedness. And second, because it's homogeneous. We have the same schema everywhere. Here's the thing. In general, when you look at NoSQL, this branch of technology, the data is nested and the data is heterogeneous. That does not fit into relational tables. You can forget it. So that means that you need to find other ways of fitting it, and somehow you can on a case-by-case basis. If I give you, for example, this sort of JSON objects, then you will see that there's nested structures, like nested arrays of objects, and you can fit it into tables in that way. You could have two tables, one table for the top level, a second table for the intermediate level. It's kind of a Dremel light, if you want, where I have two separate tables for different paths. So that works. But the problem is that in order to do that, I need it to basically reason on that very specific data set. This is not a general solution. If I give you a random data set, totally messy, completely heterogeneous, then you will have to come up with yet another solution to do that. It doesn't work. The same goes for missing values. Imagine you have missing values. You can put nulls, right? The problem is that if you have nulls everywhere, then this is not what a relational database system was designed for, right? It's not optimized for having nulls everywhere. So you see, you're already seeing the limits of that mapping in there. There's actually people who gave a lot of thought into generic ways of mapping trees to tables. Dremel is one, and there's also others. There's actually one that manages, I'm amazed how smart these people are. They managed to figure out a way of storing a collection of heterogeneous XML documents into a single table. It gives a headache to try to do the mapping back and forth, but they actually managed. But it's not going to be efficient to query. That's the thing. So in essence, whoever is trying to make, in general, JSON and XML fit in relational tables and just use existing system is basically trying to put a square peg into a round hole. Right? It just has its limit. It doesn't work. And this is why people came to the realization that you need to design new systems that do that, but they must be native systems for XML and JSON. This is what we call document stores. Right? Document store is a generic name. There's plenty of them. It's a generic name for a database system that is not a relational database management system, not relational, it's a database management system that natively speaks XML or JSON. So the idea of document stores, and these are things I'm telling you right away, but actually back then when it was nascent, it took me years to actually understand that. The way that it works is that these systems can have millions, billions, maybe today even trillions of documents in a collection. By document, I mean XML element or JSON object. It's just called the documents. Millions, billions, trillions of them, terabytes or even petabytes of data. But the thing is, each one of the documents is actually going to be small, right? We don't have terabyte documents or petabytes documents. The documents think bytes, kilobytes, maybe megabytes, but that's it. But billions of that. So the documents are JSON or XML, and here that's literally JSON or XML, right? Natively. So on the left, it's XML, on the right, it's JSON, but this is basically the idea, right? So the idea is that in your document store, you store collections of trees like that, right? So there is one tree on the top that's a JSON object, and a second tree, just to make clear the separation. You have one tree here, a second tree, a third tree, and so on and so on. In that case, it's a bit of a mess because it is unstructured. But if you actually look closer, it's not fully a mess. Look, A is an object with foo and B is an array of integers. Here it's the same. Foo object, B is an array of integers, and so on. Who would be able to write a JSON schema for this collection? Right, many of you. That's a natural thing to do, right? Foo is an integer, bar is an array of strings, foo bar is a Boolean, A is an object that has foo, that is a string that can also be null, and B an array of integers, and B is, let's say, a decimal. And then add on top of that, that foo and bar are required, and foo bar and A and B are optional. Now you will notice that here, bar in the second object is a string. So actually, it's a bit more complex than that. You would need a union of string and array to do this one, right? But just to show you an example of what a collection of trees look like. And typically, again, I repeat myself because this is important. The documents are typically small. So typically, thousands, millions, billions, trillions of objects or documents, as they are called, give you a collection. This should map in your head with RDDs and with data frames, right? In the sense of a huge number of relatively small items. Okay. Now, a first difference between the two models, and I keep saying it, is that in the case of collections of trees, NoSQL system document store, the data can be nested in a relational database management system, it's flat. And the other difference is that in a structured, structured system, it's homogeneous. So all trees look alike. On the right, they can be heterogeneous, right? So what is on the left? A homogeneous collection of trees. These are the data frames. This is something you can do with Spark SQL, right? With a bit of nestedness. What's on the right, you cannot do with Spark SQL. On the right, that will not fit in a data frame. I showed you when it pushes the problem to the user, right? If the data is heterogeneous, if you try to import it as a data frame, it's just going to fit everything into strings, and then it's on you to basically parse these strings into JSON again, right? Who has the intuition by now that a homogeneous collection of trees is basically a data frame? Right, you can draw it. Okay, awesome. That's exactly the intuition I want you to have. But you should not forget that not everything fits in a data frame. And there's plenty of collections out there that will not fit. Why can it happen? It typically happens when a company or a product is, for example, logging things. Right. For example, GitHub is logging all the commits and so on. That's the GitHub archive data set. What happens when you do that over 10 years, 20 years, 30 years, maybe 40 years, is that you keep changing the format with which you log. Every couple of years, you're going to add a field, remove a field. You're going to say, okay, that's no longer a string, it's an integer, or I changed my mind, it's a string again, now it's an array of integers. So every couple of years, the schema changes. But when you keep logging the data, people are not going to convert past data to the new format. They keep it. So as the years go and go and go and go, you end up with a huge mess. Well, every couple of years, you have a different format. And when you try to query the whole 40 years of data, it doesn't fit in a data frame because you don't have the same types. For whom is that clear? That's a typical use case, the logging. And we're stuck because we cannot use Spark SQL to do that. But document stores actually are here to solve that problem. So document stores are really, really good at dealing with that sort of data on the right, that is heterogeneous. You can project things, you can select things. I will show you how. You can aggregate things. The one thing that document stores do not really do at least not efficiently or even not at all for many, is joins. They will not even let you do joins. Joins, basically, if you really, really want to join data with a document store, you will have to re-implement your own join in C++ or Java or whatever host language, but you'll have to do it yourself. Actually, people do that. Some people re-implemented joins precisely because the document store doesn't do it. Okay, so they are focused on projection, selection, and aggregation. Okay, now they still allow you, these document stores, to validate the data after you populate it. You can basically, just like in a data lake, you can import a heterogeneous collection of JSON documents or XML elements. And after that, you can choose to validate. And then it will show you, okay, these are the documents that are not valid. Then you can fix them, or you can adapt your schema in order to make them valid and so on, right? So it's a trial and error thing at that point. You can also explore. The data discovery is also an interesting area where you basically get a data set that you know nothing of, and you have to discover its schema. So these tools are actually useful for doing that. There are plenty of document stores around. It was actually a big hype. I think maybe 10 years ago was the big hype. There was barely any blockchains back then. We were barely out of the key value store hype. That was, everybody wanted a key value store back then. And then there was this era of the document store hype, where companies were getting billions of dollars of investments in order to develop their products. The mostly used products, who knows some of these products? Okay. Many of you know MongoDB. MongoDB is the most popular one among the document stores. This is the one we'll take, that I will show you how it works. What you need to understand is that these document stores are typically either JSON or XML. MongoDB is JSON, CouchDB is JSON, Elasticsearch is JSON, ExisDB is XML, Cloudon is JSON, ArangoDB is JSON, MarkLogic is XML and JSON. They kind of do everything. Azure also has a few products that do both, and BaseX is again XML, and there's many others, right? So some of them are specialized in XML, some of them are specialized in JSON, so that's why it's important to know both of them. MarkLogic, you might have heard a few years ago when the American government introduced what is known as Obamacare, they actually needed a database, and MarkLogic was one of the selected providers for the implementation. Okay, so this is going to be our focus. It's going to be MongoDB. I will show you how that works. This is totally different. Think of it as something of its own, independent of HDFS, independent of HBase, independent of Spark. It has nothing to do. It's completely disconnected. It's a thing of its own. And it's closer in spirit to PostgreSQL than it is to Spark, because MongoDB is really a product that you install and you import your data in there and you query it just like you would do with PostgreSQL. Okay, now a few words on the encoding, because this is something I haven't said much before, but basically every system in the end encodes things as zeros and ones. You're computer scientists, so I probably won't spend much time on this. What is important is you have several character encodings that give you a way to map these characters to bits. By now, what's very important for every new product you might start, think international from the very beginning. You should not even use any more ASCII, ISO Latin 1, and so on. Forget about them. Always go UTF-8, UTF-16, and so on, right? It's based on Unicode. It's a standard with all the letters and so on. And then you're basically ready for any language in the world, because this all gets encoded in there, right? So this is here the main message, that by now, I think most documents use UTF-8, maybe UTF-16 for some of them. So whenever you create a JSON document, CSV document, an XML document, always use by default. If you don't want to think too much, just go for UTF-8. Okay, ASCII, it's actually almost textbooks, now history books. I think you've seen that many times, but these are the very, very early days of computers, where English was the dominating language. And so it's a simple enough language. There's no accents, nothing. So it was all designed with these 128 characters. But now we can go beyond that. So let's see pi, for example. Pi would be in the Unicode catalog. So if you look it up, it's 03A0 in base 16, and you can encode it in UTF-8 like that. So here's how it goes. this is the Unicode number in the Unicode catalog. This is the base 2 equivalent. This is just the base 2 of this. This is 3, this is A, and this is 0. What you do is that you basically have this 1, 0 that is a marker that this is the continuation flag, and this is the first packet. But then if you look at this corresponds to the bits right there. You basically just cut it into multiple packets of 8 bits, and it's elastic. The ASCII characters are going to fit on just 8 bits, and the more complicated characters will need 16, 24, 32 bits, right? Who is already familiar with UTF-8? I think many, okay. So basically, use UTF-8. But what did I want to say about encodings? I wanted to say that you could store JSON or XML as text, but it's better to store it as a binary for efficiency. We've already seen that with Parquet. In the case of a document store, MongoDB stores it in BSON. So when you have a JSON object, foo null, for example, is a JSON object, it's not going to store it as curly brace, quote, FOO, and so on. It's instead going to store it efficiently with the characters that you see below, which basically, at the start, you have, I think, what is a length, 6. So there are 6 binary packets, right? These are, I don't want to make any mistake, these are bytes. So you have 0.3 that tells you here's an object. 6.6 is F, 6F is O, so FOO, right? If you start an object, what comes after that is the first key. So 0.3 tells you it's an object, then you have FOO. 0 is the termination of the string, right? Then you have 0A that tells you that's a null, and 0.0 that's the termination of the document, right? Of the object. So of course, there is a standard, there is a specification. Actually, if you're interested, you can go to bson-spec.org, where they actually give you the complete mapping. You don't need to learn it. All you need to understand is that basically it stores JSON documents in a more compact and efficient format that is a binary format like this, right? It's going to be much smaller. But the difference with Parquet is that here you don't need a schema. With Parquet, you need a schema if you want to store it as Parquet. Here you don't. Doesn't matter. This can store absolutely any JSON object. BSON actually goes a bit beyond in terms of types, because normally in JSON you only have strings, numbers, booleans, and nulls. But BSON has a few more types. It supports dates. It supports, for example, binary data and so on. So it adds a few types along the way. That MongoDB is going to support. Okay, so now in MongoDB, the stack looks like this. MongoDB stores its data as BSON after you have imported it. And then it reads that data as well-formed JSON. Then you can choose if or not you want to validate it, and then you can query it with the syntax. Okay. But I think you all want to see how it works, right? Because I think I've talked enough on the introduction. So let's go ahead and query it, right? So you need to understand that it's an ETL-based system in which we import the data. So in MongoDB and most document stores, you have the CRUD approach with create, read, update, delete. And here it goes. Imagine you have a collection and you want to find people in there. So you say db.scientist. So scientist is the name of the collection. And then .find is your main function in order to do your queries. If you want everything in a collection, you can either use open parenthesis, close parenthesis, so no parameters at all, or you can pass an empty object. This is equivalent, and this returns the entire collection. Now, several words about that. This here is JavaScript. MongoDB is using JavaScript on the shell. If you open the shell, it also has pilots in other languages. You can also use Python. You can use Java, C++, and so on. So you can install drivers and then interact with MongoDB. I'm going to show you JavaScript today because that's what most people know regarding the shell. But you shouldn't be surprised if you use Python, the API might deviate a bit. Right, so you just need to be aware, especially if you look up documentation, that might slightly differ. But at the exam, we will only have theoretical questions. We won't have any programming questions on MongoDB, right? So the programming question, it's mostly going to be SQL, Spark RDD, Spark SQL, JSONic, and that's it. Okay, the other thing I want to say is that I put on the top right a SQL cheat sheet. What is that? it's an equivalent query of what it would look like to do the same in SQL. It's just in order to help you make the connection about what it does, right? Something else that I can say is that when you import your data, you can use tools. There is a command tool to import from a huge JSON lines files, for example, or JSON files. What MongoDB is going to do is that it's going to put an ID, an object ID, that's basically a primary key that it just generates on the fly. That's just, think of it as a big integer that it adds to every object. So I will not put it on the screen, but you would see it on the shell as underscore ID, right? So this is the primary key of your collection. Okay. Now let's start doing things. So if you want to select something, you want to read all the documents that, for example, have theory associated with relativity, then you can supply a JSON object to that function find that says that you want to select on that. And you can see that in these 4 documents there, the first one and the fourth one are selected because they match theory relativity. 2 and 3 do not match, so they are not going to be returned, right? So this returns, assuming this is a collection of 4 objects, this is going to return the first and the fourth objects. You see an equivalent SQL query up there, which is the where clause. You know, you do selections with the where clause in SQL. So this is like select star from scientists, where theory equals relativity. Who is with me? Okay. Now, you might have noticed something. This here is not a query language. What you see here is not a query language. This is an API within a host imperative language, Python, JavaScript, and so on. It's very important to understand this difference, right? So this is why, as the queries are going to become complex, you will see a lot of parentheses and curly braces, and you know, and then you will see that it works for simple use cases. Then you start reaching limits again because it's only an API and not a real query language. A real full-fledged query language we'll see next week, right? But a lot of people basically work in that way using Python or JavaScript. Typically, they are going to have that behind a website. So basically, it's whatever language they use for the website, PHP or C++ or Java. In that language, they are going to invoke MongoDB queries like that, and they process everything in the host language. Okay, now we had selection. Let's do projection then. Projection is done with a second parameter. So the first parameter is for the selection. Second parameter of finds is for the projection. And you need to supply what you want to project on with a 1 if you want to include it. 0 would be for excluding, 1 is for including, right? So here you project on first and on last, first one, last one, and you only return this first and last. It would be in SQL the equivalent of putting these columns in the select clause, right? Now you see the complexity popping up, right? It's very verbose. Again, that's really an API. It's an API that tells you how to call this function find in JavaScript and get what you want. Okay, you can project away with 0 instead of 1. There is not really an equivalent in SQL. In SQL, there's no way of saying I want everything except this and that column. You cannot do it. In MongoDB, you can, and you can say I want everything except theory, right? And then this is going actually for that collection, it's the same results, but this is another way of doing it. What you can do, for example, with this is that if you don't like the ID field, because by default, it will always return the object IDs, but that will pollute your screen. So you can project it away by adding underscore ID 0. And then you get rid of the object ID on your screen in the shell. You can mix ID 0 with fields set to 1, but you cannot generally mix, meaning that MongoDB will not let you use 1s here and there and 0s here and there. It's either you use 1s everywhere or you use 0s everywhere. Either you project or you project away, right? The only exception to that rule is the object ID. You're allowed to project away the object ID while projecting other fields. Okay? Yes?
There's a question on Zoom. What if the thing we filter is an integer?
What is it?
What if the thing we filter is an integer? Oh, so what would that look like?
Okay, so theory, for example, right? So let's say theory is an integer. That's not going to be included then in the answer. And that's a very good question because indeed, your collection might be heterogeneous. It might be that in some documents, theory is going to be a string. In some other documents, it's an integer. In some other documents, it's an array. In some other documents, it's a nested object. What this query does is that it really returns when it's the string relativity. Everything else is just not included in the selection. And this is something original to document stores, because that's a problem you don't have in a relational database, right? Because in a relational database, you know that everything in a column is of the same type, right? So that's a very good question. And indeed, it must match the type here. That's really the strings relativity. Did I answer your question? Yep, awesome. Okay, so you can project, or you can project away, and this is a new thing that we don't have in SQL. Okay. Now you can also use a conjunction of filters. That would be an AND in SQL. Select where, and then it's just a predicate. The way it's done in MongoDB, again, that's part of the API, is that you just have this object that you supply for your selection, just add more keys. And it's a conjunction of all of that. So if you have this object theory, relativity, last Einstein, it will be an AND between the two. It both must be that the theory is relativity and last is Einstein, and then you would only select the first one, right? So that would be an AND in select from where. So you start seeing here the limits of an API, because in SQL, what you put in the where clause is a very generic thing. It's any expression, any predicate can go in there. Here you see in the API, you're a bit constrained. It has to be a JSON object. If you want to have something more complex, you start running into these things, right? So you see, we start hitting the limit of what we get with an API. Because in SQL, if you want an OR, a disjunction, you just use an OR, right? It's almost the same query, and OR. But in the case of MongoDB, in the API, you need to use this dollar thing, it's dollar keywords. And here it's $OR, which is an array, but that's part of the API. It's not an array in the data. It's an array in the API of MongoDB. So $OR is an array of everything you want to do as a disjunction. So here we're saying either last is Newton or last is Einstein, and that would select the first two objects. For whom is that clear? Right. Who starts having an intuition on the limits of an API versus a query language, right? That a query language is more flexible, and an API, you probably need to spend more time in the documentation looking up the way to do it. Yes?
Can we have and within or? So
yes,
like
absolutely.
nested. Yeah.
Absolutely. You can have or here, and last Newton, you can have several keys. That will be an and, right? That would called ends within an or is, I think, a disjunctive form in logic. You know, when you have a logical formula, you can either express it in a, I'm not sure it's the exact terminology, but disjunctive normal form or conjunctive normal form, right? You can always write it in one way or the other. So you can indeed have a $OR with nested ends. The opposite, how would you do nesting the ORs in ends? It might be there's a $end. We will check. It might be there's a $end that also allows you to do that. Yeah. Okay. Is there another question? So just so only the second arguments. Ah, okay. All right. Let's check the time. I think that's still have a few minutes left. Okay. So since we started with these dollar things, we can actually test for something else than equality. And again, because that's an API, it's more complex than in SQL. In SQL, it's just about using a different comparison operator. Instead of equal, you have greater than or equal. But in MongoDB, if you just say something, it's equal. If you want something different, then you need to have this $GTE, right? So this is where it starts, to be complex. So publications must be greater than or equal to 100, right? Yes? Or maybe you could speak in the catch box so people hear you. Yeah. Let me increase the volume, maybe. Where is it connected? Oh, it's there. Let me see. Can you speak now?
Yes, apparently. Nice. So my question is about...
Try again.
Okay, so my question is about querying arrays. So for instance, if our theory, instead of single theory, would contain like array of theories. So for instance, like, I don't know, Isaac Newton gravitation and motion, and we want to get like one of them. So at least one of them.
I think, let me try to find, I think I have a, this is the opposite. Let me try, I think I had a slide somewhere.
I think it's here.
That's this one. Yes, that's the slide. Yeah, that's your question, right?
Exactly.
Okay, yeah, indeed. So here's what happens. You have indeed an array and you want to test for the arrays that contain one value. Again, it's an API thing. It's not something you can guess. This is only something you know if you read the documentation, that if you put a string in there, if it's an array, it's going to implicitly try to go inside the arrays and see if it finds the element in there. This is what it does, right? But again, you cannot guess. This is something that is part of the API, and it might be that a different document store is going to do things differently, right? Does it answer your question? Okay, there's another question over there. Maybe if you throw the catch box.
If it's an array of arrays, does it go 2 levels deep?
Oh, that's a good question. I'm not sure. Could you make a note that we check? That's a good question. So again, you see, the reason I cannot tell you is that it's really an API, and these are really decisions that were made by the engineering team. This is a bit the intuition that I want to give you here. I want to give you the intuition that many systems have an API like that, but an API and a query language are not the same thing. And I hope that at the end of the course, you realize that a query language is really the Rolls-Royce of how you access a database. Okay. Did I answer your question? Okay, awesome. Let me check the time. I think we are almost there. So I will continue to show you the other aspects of the language. So greater than. Maybe we stop here where, what if we have missing fields? That's totally fine. For example, if you look for theory relativity, then it's not going to return the documents that miss a field theory, right? So you see that it has this flexibility. One more thing I want to say on GTE, on the order, is that normally in SQL, you only compare the same type. You compare integers, you compare numbers, you compare Booleans, and so on. In MongoDB, it actually has the notion of comparison across types, right? So there is a list of types. For example, I don't have it in the top of my mind, but it's something like every number is smaller than every string is smaller than every array is smaller than every object. So it means that these GTE things, they are always going to succeed, even if the types are incompatible. It's just using this cross-type ordering. It's totally arbitrary, but this is how you break the wall between types, and you can deal with a heterogeneous system, right? Let's stop here, then we'll continue next week with this. Who has the feeling they get it, what a document store is, what a query language, what an API looks like? Okay, very good. So thank you very much. Enjoy the exercises, especially the coming 2 weeks on Spark, Spark and Spark SQL. And I'll see you next week in CAB again for the continuation of document stores. Thank you very much. Have a good day.